Okay, good morning or good afternoon. So this presentation summarizes several researches on the indoor thermal environment in highly insulated residential buildings in Norway, and especially on the need to create colder bedrooms with warm living areas. So, okay. So first we can start with a general description of temperature in bedrooms in Norway. So whatever the insulation level. So in 2017, so 1,000 Norwegian adults have been part to a survey. So as we can see, 70% of the person reported that they have a temperature below 18 degrees Celsius in their bedroom. So many would like also a temperature below 12 degrees Celsius, and especially for people above 45 years. So this need for colder bedroom can be less severe in other countries because 12 degrees is very severe. But other references taken from Scandinavian, for example, show that the need for colder bedroom is also present in other countries. So in the same survey, occupants reported on their habit regarding window openings in bedroom. And as you can see, a large number of occupants keep the bedroom window opened all the time, including the winter. And again, this behavior is more pronounced for people older than 45 years. So we can now discuss the temperature zoning, meaning the difference of temperature between the living areas and bedrooms, in the specific context of highly insulated residential buildings. So the temperature zoning is limited in these highly insulated buildings because they are built with highly insulated external walls and high performance window. And secondly, these buildings are equipped with balanced mechanical ventilation with an efficient heat recovery unit. So the temperature of the supply ventilation air is, at least in Scandinavia and Norway, is the same for all the rooms, meaning, for example, the living room and bedrooms, so that we can call this ventilation strategy one-zone ventilation. So when discussing temperature zoning, it's important to take the building construction mode into account, meaning the difference between lightweight and heavyweight buildings. So in lightweight buildings, the partition walls are often insulated for acoustic reasons. This leads to lower heat transfer coefficient for partition wall in lightweight buildings. And this is beneficial for temperature zoning. So in Norway, many buildings are lightweight construction in wood. We can now summarize the research regarding indoor thermal environment in Norwegian passive houses. So it is based on questionnaires, interviews, and sometimes on field measurements with 100 of buildings. So regarding bedrooms, many occupants want colder bedrooms, so mainly meaning colder than 16 degrees Celsius. And very importantly, 50% of the occupants open bedroom windows several hours every day during winter time. And the main motivation for this is temperature control and not indoor air quality, so keeping the bedroom colder. It's also shown that many occupants do not control the temperature of the supply ventilation air correctly to get colder bedrooms. So they keep the supply air temperature relatively high, even though they would like cold bedrooms. And regarding living areas, so it has been already mentioned by Kari that the desired indoor temperature is often between 22 and 24 degrees Celsius, and that in general the satisfaction is very high regarding the thermal comfort in living areas. So to illustrate this, we can take the example of two flats we studied, taken in an apartment block. So the insulation level is given in the table. So we can see that the internal partition walls are quite well insulated. And in this case, it's a decentralized strategy. So each flat has its own air handling unit with the heat exchanger. So the indoor temperature, as well as the opening of the windows and internal doors, have been measured for a period of 2 weeks in March. So what we can see is that in the living room and corridor, the temperature is 20 degrees when the occupants are not there and 24 degrees Celsius when the occupants are present. While in the bedroom temperature is oscillating around 16 degrees Celsius, and the bedroom window is constantly open here during a period of 2 weeks. And coherently, the occupant have closed the bedroom door. So if the occupants not operate the ventilation system correctly, the question is to know whether one can get these cold bedrooms without window opening by applying a correct control. And to answer to this question, we have used a calibrated detailed dynamic simulation, meaning multi-zone simulation performed in INIVE with what we call an embedded ventilation network model, so that airflows between the rooms and the outdoor can be computed by the model. So the case reported in this slide is a case where the living room temperature is at 21 degrees Celsius, and the target is to reach a temperature of 16 degrees in the bedroom or even lower. So if you take the baseline control or way that the building is operated, like in measurements, we have space heating needs, so the figure on the right, that is close to 15 kilowatt-hour per square meter and per year. But if we look at the temperature, so the red curve on the left figure, we are still far from the 16 degree in the bedroom. So the temperature difference typically is of 2 or 3 degrees Celsius between the bedrooms and the living areas. If we do not have a heating battery, so that's the scenario in magenta, the temperature in bedroom is decreased and the space heating needs is also slightly decreased, so which is good, but we are still far away from the 16 degree in bedrooms. We can then decrease the temperature set points for the heat recovery unit, for example, 16 degree or 14 degrees Celsius. So kind of artificially reducing the heat recovery efficiency. And with a set point of 14 degrees Celsius, so in cyan, the temperature in bedroom is getting close to 16 degrees Celsius, but the space heating needs is increasing quite a lot for that case. Alternatively, we can open the bedroom window to reach 16 degrees Celsius, and in this case, so the blue curve, we get quite increased space heating needs as well. So we can have some general conclusion based on this research. So we can have a sketch like this to represent it. So we can start with a uniform temperature in the building. So the point 0 in this graph, and the x-axis is the temperature zoning. And we can start at 0 where the temperature is uniform in the building. So then we can apply a moderate temperature zoning in the building, but just not heating the bedrooms and keeping the internal door closed. And this has a positive effect on the space heating needs that are slightly decreasing. But if we would like larger temperature zoning, and in our case, with lightweight construction, it corresponds to a temperature higher than typically 3 degrees Celsius, we need to introduce a heat sink inside the building, meaning that we need either to open the bedroom windows or to decrease the effectiveness of the heat recovery unit. So it corresponds to degrading the thermal performance of the building and then to a rapid increase of the space heating needs. So what we should investigate is that if it's possible to get a very large temperature zoning, a large delta T, without increasing the space heating needs a lot, for example, by improving the ventilation strategy. So again, the research shows that control alone cannot decrease bedroom temperature significantly without large increase of the space heating needs. And something should be changed in the building concept itself, like the ventilation strategy. In this context, we can formulate 2 questions. First, what is the relative importance of ventilation and heat conduction in partition walls in this increase of the space heating needs? And the second question would be, how alternative ventilation strategy could improve the energy efficiency with large temperature zoning? So To understand the physical problem, it can be simplified as follows. So we can divide the building between heated zone and unheated zones. We look at the heat transfer between these heated zones and not heated zones, P, and it has one contribution from heat conduction through partition wall and one contribution from the ventilation air that is transferred from colder bedroom to warmer living areas, so V2 in this graph, so due to the cascades principle. So the point is that if we decrease a lot the bedroom temperature, for example, using bedroom window opening, this heat transfer P is increased, and then the space heating needs increase as well. So there are two contributions: heat conduction, partition wall, and ventilation. So to reduce this increase of the space heating needs, we can look at alternative ventilation strategies. So if this one zone ventilation with cascade ventilation is strategy A, we can have a strategy B, which would be the same strategy, but we are shutting down the mechanical ventilation system when in bedrooms, when people are opening windows in bedrooms. We can have a strategy C, so which would be to have supply and exhaust in bedroom balanced, to remove the cascade ventilation to avoid reheating of the air transferred to the heated living areas. And finally, we have like a decentralized ventilation. Here, decentralized means that we would have air handling units dedicated to bedrooms or to one bedroom, and the rest of the building, the heated area, with dedicated air handling units. So to investigate this, we have made a simulation study of a detached house in Oslo. We consider different construction modes, lightweight to heavyweights. So we consider CIV ventilation with pre-accepted airflow rates from the building regulation, Norwegian Building Regulation Text 17. So it leads to different nominal airflow rates for the different ventilation strategies from A to D. So to answer to the first question, practically, without entering into the details, it means that we need to perform a steady state simulation. So we apply a constant outdoor temperature to create like typical temperature differences in the building. We consider different type of construction, heavyweight and lightweight, and different temperature set point in the living area, 21 and 24 degrees Celsius. And what we monitor in this graph is the increase of the space heating needs due to window opening in bedrooms to reach 16 degrees Celsius, or any kind of strategy of heat sink to decrease the temperature in bedroom. So the conclusion regarding the importance of ventilation is the following. So for heavyweight construction, the heat conduction effect in partition walls is larger than the ventilation effect. So you can see it when you compare the yellow bars to the red bars. But for lightweight buildings construction, the heat conduction and ventilation effect have the same order of magnitude. So a second conclusion, it can be done by comparing the ventilation strategies. So the strategy B and C leads to a moderate reduction of the ventilation contribution to the increase of the space heating needs. So we see that the red bars are not reduced a lot in B, C compared to A, while that for the strategy D, we remove completely the influence of ventilation in the increase of the space heating needs. While this effect of the heat conduction through partition wall in yellow stays the same for all the ventilation strategies. So regarding the second question, so the energy efficiency can be analyzed with yearly simulation. Here for this graph, we just use lightweight construction with a living room temperature of 24 degrees, and we compare different control strategies. So if we take the cases with closed bedroom, bedroom windows, in fact, the strategies without cascade ventilation have higher nominal airflow rates compared to the baseline ventilation, and this is due to the fact that we use pre-accepted airflow rates from the building regulation. So consequently, with closed bedroom windows, we have slightly higher space heating needs for strategy C and D compared to the strategy A. So if one is not interested into large temperature zoning, like more than 3 degrees that we consider here, alternative strategy C and D are somehow less energy efficient. But now if we open bedroom windows, we can see that the space heating needs increases for all the ventilation strategies, but that this increase is slightly lower for strategy B and C than the strategy A, and that the strategy D has a significantly lower increase of the space heating needs compared to the strategy A. So in conclusion, so our work focused on highly insulated residential buildings with one zone balanced mechanical ventilation. And researches show that a significant increase of the space heating needs with a large temperature zoning. And here we speak about temperature differences above 3 degrees Celsius in case of the lightweight constructions. And the simulation showed that it's not a question of control. Something in the building concept should be changed to allow large temperature zoning. And it's important because a significant part of the Norwegian population, and maybe in Scandinavia, would like colder bedroom, meaning lower than 80 degrees Celsius. Some important remarks should be made. So firstly, we did not present results with a buffer zone, so a zone with an intermediate temperature level. So our simulation showed that it performs very well for temperature zoning and energy efficiency, but it's not sure that all occupants can accept to use a significant part of their house for this purpose, especially in flats. So that's a question of area effectiveness. And the second comment is that if you're working in a country where there are a lot of heavyweight buildings, the temperature zoning can be even more complicated to do. So regarding the energy efficiency with large temperature zoning, we have shown that heat conduction is dominant for heavyweight buildings and that ventilation has the same magnitude of effect as the heat conduction in partition wall for lightweight buildings. So the main conclusion for us is that the ventilation strategy can help, but it will not solve the problem alone. So it should be a combination on ventilation and maybe some measures on the building himself. For the second question, we can say that the ventilation contribution can be moderately reduced with the strategy B, so shutting down the supply ventilation air in bedrooms of the mechanical ventilation when bedrooms windows are open. And also for the ventilation strategy C, so where we balance airflows in the bedroom, so it has a moderate effect to improve the energy efficiency with high temperature zoning, while that for decentralized ventilation, so meaning one air handling unit for the bedrooms, then we have a significant improvement of the situation, and this should be maybe one, at least based on our studies, one of the main promising approach in this respect. Okay, so thank you for your attention. So this is the list of the references.